So it's a great pleasure to have Rajath from ICTP to us there, and he'll tell us about constraints on non-invertible symmetries in 2+1D. Please take it away.
Okay, thank you. Thank you to all the organizers for this opportunity, and let me take this stage to thank them for this Symmetry series, because I have learned a lot from this series, and I'm happy to contribute to it. So today I would like to talk about some constraints on non-invertible symmetries. These are non-invertible symmetries implemented by surface operators in 2+1D. And the idea is to look at the action of these surface operators on some line operators and try to constrain the existence of non-invertible symmetries in a precise way. And I have taken the liberty to not define some aspects in the slides, but please ask me questions if something is confusing. So let me begin by some motivation. So we know that we have been thinking about symmetries, generalized symmetries and non-invertible symmetries in terms of topological operators of various dimensions. And a full study of symmetries requires us to understand the full algebraic structure, that if there's a finite symmetry, then we have a algebraic structure which captures that symmetry, and we would like to understand various aspects of that algebraic structure. So in particular, we would like to understand these higher fusion categories that describe symmetries in various dimensions. And the classification of these higher fusion categories, like compared to classification of groups, is quite hard. But there are cases where we can make progress in the classification. And one case is this rank finiteness, where there's a theorem that if we have a finite number of topological line operators, then they admit a finite number of fusion rings. And for each fusion ring, you have a finite number of fusion categories. So there's a finiteness in the number of fusion categories, braided fusion categories, for a given number of line operators. And using this, we would like to classify them, at least for low rank. So that is one thing. But this is about line operators. We can ask about higher dimensions. In 2+1D, we have surface operators and line operators. So we have certain higher categories in the picture, and we can ask what are some constraints on them, on the structure. So one particular constraint that I would like to focus on is this statement that if we don't have topological line operators, then surface operators must be invertible. So some of the questions that I will try to ask in this talk and answer are motivated by this result. So let me actually go through this statement and try to argue why this is true. So the basic idea is to start with some topological surface operator, and we can shrink the surface to some line operator. So that is the basic operation that we use. And this LS that we have here may not be a simple line operator. This line operator will in general decompose into some sum of lines. So when we shrink a surface to get a line, this line will decompose into a sum of lines. And among the sum, we will have, in general, we'll have the identity line. And the question is, how many copies of the identity line can be there in this line LS for a given surface? So to understand that, let us try to look at a junction between this LS and the identity line. So alpha is a point, it's an operator that can exist at this junction of LS and the identity line. And we look at this configuration, and what we try to do is we replace this line LS here with the surface. So suppose we kind of blow up this line into the surface. We have this particular surface operator here with the identity line forming a junction, and the junction is labeled by alpha. So alpha belongs to this particular space, and the number of this alpha, the dimension of the space, essentially counts the number of identity line in this LS. And once we get this, we can kind of flatten this surface to get the surface operator with the identity line ending on the surface. So for each alpha, we get a different way in which the identity line can end on the surface S. But we can essentially forget about this identity line and think of this alpha as a local operator on S. So if there are different ways in which the identity line can form a junction with LS, there are different non-trivial local operators on S. So if we focus on simple surface operators, so these are surface operators which do not have any non-trivial local operators on them, shrinking those surfaces should give us an LS in which there's only one copy of the identity line. So that is the takeaway from this, that there's only one copy of the identity line whenever we shrink a surface, a simple surface. So this is what we can use to then argue that if there are no line operators, surface operators must be invertible. So suppose there are no non-trivial line operators, then when we shrink any surface, any simple surface, when we shrink, we always get the line that we get is always the trivial line, because we only have the trivial line and we can only have one copy of the trivial line whenever we shrink a simple surface. So using this, we can then consider a fusion rule. So suppose we have some non-invertible surface S, which has some kind of non-invertible fusion rule of this type. So S fusion with S prime is some sum of surfaces. And in this, we can shrink each of the surfaces that form this fusion rule and replace it with this LS. So replacing these surfaces with these lines, we get a fusion of line operators is equal to sum of line operators. But each of these lines are just the identity line because we only have the identity line. So this gives us some inconsistency if the fusion is non-invertible. So when we have only the trivial line, when we shrink simple surfaces, we only get the trivial line. And in that case, we cannot have non-invertible surfaces. So this is the result. So I would like to motivate some questions based on this result. But if there are some questions on this, please ask me. Okay. So this motivates us to ask some questions, and those are the following. So we learned that if there are no line operators, then we have only invertible surfaces. But we can ask, if there are line operators, are we guaranteed to have non-invertible surfaces? And this is not true. One example is U1 at level 2 Chern-Simons theory, where we have a non-trivial line operator, but this theory doesn't have any non-invertible symmetries or even invertible symmetries. So this example shows that this cannot be true. But we can ask, is there some way in which the data of topological line operators can it constrain the invertibility of surface operators? So given a set of topological lines and its data, how can we constrain surface operators which act on these lines? So that would be one question. And in 2+1D, many non-invertible symmetries come from condensations of line operators. We can ask a related question: what is the condition for a condensation defect to be invertible? So if you start with a set of line operators, condense them on a surface, produce a surface operator, what determines the invertibility of that surface? Also, in this context, we can ask another question, which is, if we have some QFT which has a set of non-invertible surfaces, we can ask if there is some topological manipulation of this QFT Q, which takes us to Q prime, such that the image of these non-invertible surfaces in Q prime are invertible. So the non-invertible symmetries in Q are kind of replaced with invertible symmetries through this topological manipulation. And we can ask whether such manipulation exists. If then one terminology that will be important is that if this manipulation exists, then we will call this non-intrinsic non-invertible symmetry, following these papers here. And another thing that I would like to mention is that if phi inverse, so phi is this topological manipulation, phi inverse is some inverse for that, which takes us from Q prime to Q. And if phi inverse is gauging a finite group, then we will call this non-invertible symmetries group theoretical, because it is obtained by this phi inverse, which is gauging a finite group. And it is important to distinguish these two, because we will see examples where some symmetries are non-intrinsics, but they are not group theoretical in this definition. So these are some questions that we would like to address in 2+1D. Okay. So the structure of the talk is as follows. Because we are interested in surface operators which have some action on line operators, and we would like to use that action and the data of the lines to constrain surface operators, a natural starting point is to look at Chern-Simons series or TQFTs, where we have line operators and surface operators. So I will start with abelian TQFTs, the simplest case, where we can try to define what we mean by a non-invertible surface in a particular way that I will explain, and also try to constrain them. Then I will try to relate that definition to condensation and try to explain some aspects of condensation defect. Then I will go on to non-abelian TQFTs and try to prove and argue for similar results in non-abelian TQFTs. And finally, I will go to generic QFTs, try to make some comments about what this means for generic QFTs. So this is the outline of the talk. Any questions at this point? Yeah.
Yeah, I have a question. Can you go back to the last slide, please?
Yes. Yeah.
Thanks. So I had two questions about this slide. The first is, on the last bullet point, you say such that phi are invertible surfaces. Are you allowing for there to be non-invertible lines?
Yeah, that's right. So here, whenever I talk about non-invertible symmetries, I am focusing on non-invertible surfaces or invertible surfaces. Lines just come along with the description. The lines can be non-invertible. So in Q prime, the lines could be non-invertible. Yes.
Okay, thanks. And then my second question was, if phi inverse is giving a finite group, or will you allow it to be a two group, or does it have to be an ordinary group?
It could be a two group. Yeah.
Okay.
Yeah.
Okay. Thank you.
Could be. Yes. Yeah.
There's another question. David Costa, can you unmute yourself?
Yeah. So, does your argument in the previous slides about like shrinking the surfaces into lines generalize to higher codimension objects? I think because I have some examples in mind, and I think it should not, but I can't see where it breaks. You have any comment?
I think there are some similar results by the same authors where they describe this in higher dimensions, but these are for specific operators. So in 4 dimensions, let's take, their surface operators are always you can always do this procedure, right? Where you can always condense all the lines in 4 dimensions up to a transparent fermion. And in that process, we'll make all the surfaces invertible. So in that sense, for the same dimensional operators, this statement holds in 4D as well. But you can ask for membrane operators and other kinds of operators. And I think these authors have a similar result. Sorry, something is, okay. Yeah, so I think these authors have a similar results in high dimensions, but I don't know what class of operators this applies to in general.
Okay, thank you.
Yeah. Okay, so let me start with a very quick review of non-abelian TQFTs. So we have a set of line operators in the theory labeled by A, B, etc. And we will have some fusion rule, in general non-invertible. And we have some, the fusion rule is associative and commutative. So we have some fusion and braiding matrices, which allows us to move between these diagrams. So associativity is controlled by these F matrices, and commutativity is controlled by these braiding matrices. So this together, we have this data forms a modular tensor category. And this is the full data of, and these F and R, of course, have to satisfy certain conditions. I will not be using those conditions explicitly here, so I won't mention them. These F and R matrices for a given fusion ring satisfying those conditions forms a modular tensor category. And we will first look at abelian TQFTs, where this structure simplifies a lot. So let us look at abelian TQFTs, where we have a set of line operators again, but now the fusion rules forms a abelian group. It is not a ring. And in this case, the data that describes the modular tensor category is just given by some topological spins. So we associate some root of unity to each line operator. And we should associate roots of unity in such a way that this braiding matrix is non-degenerate. So this should be an invertible matrix as a matrix. And these topological spins correspond to invariance of this diagram here, and the braiding corresponds to invariance of the Hopf link here. So in this case, we have a description of the TQFT in terms of these basis independent quantities, these sum complex numbers, and such that this is an invertible matrix. So with this data, we would like to define what we mean by a symmetry of this data. If it is an invertible symmetry, it should be some action on these line operators so that these physical quantities are preserved. So what's the definition of a symmetry in this case? So for an invertible symmetry is some permutation of the line operators such that we preserve the topological spin and we preserve the S matrix. So this is one way to say. This guarantees that this permutation is an automorphism of the fusion group. So we can either define the symmetry as an automorphism of the fusion group spin, or we can say that it preserves twist and S matrix. So how do we look at this pictorially? So we have some surface operator S sigma, which implements the symmetry for us. And we have some A, which is permuted to some other line sigma A under the action of the surface operator. Now, compatibility with fusion can be seen in the following way. We have two line operators. Here we have A, which is getting mapped to B, and C getting mapped to D. And we can fuse these lines along with the junctions on the surface. So we have A times C getting mapped to B times D. So if this configuration here is non-trivial, we want this to be non-trivial. And we have compatibility with fusion in this sense. So this is the definition of invertible symmetry. And we would like to generalize this to a notion of non-invertible symmetry. So for non-invertible symmetries, in general, so the idea is that the action on the line operators may not be a permutation anymore. In particular, we could have some simple line operator here, which is getting mapped to a sum of lines. So a simple line can get mapped to a sum of lines, which is a non-simple line. So how do we understand this action diagrammatically? So the idea is that we have this action on A, which is a sum on B, and NSAB are some integers, which tells us whether how many copies of B can appear in this action. And pictorially, we have some diagram like this, where we have A getting mapped to B under the action of the surface. And this is true when NSAB is non-zero. So if it is non-zero, we have this action like this, which tells us that A and B can form a junction on the surface. And the possible junctions belong to some vector space. And the dimension of that vector space is given by this integer. So this is like when we consider junctions of line operators, but now junctions of lines with surfaces. There are some special cases where, suppose we have NS acting on A is B, NS acting on A to give B is 0 for all B. We could have something like this, where a line is set to 0. What that means is that this line A cannot form a junction with the surface for any choice of B. So the line cannot form a junction with any other line on the surface. We could have something like NSA1 equal to 0. Not equal to 0. And this is the case when we say that the line A can end on the surface, because on the other side, we have the trivial line. So when it is non-zero like this, we say that A can end on the surface. When this action is 0, we say that this A cannot end on the surface. In general, we have some non-trivial A and B, and we say that A and B can form a junction on the surface. So we would like to study such actions. But in the case of invertible symmetries, we constrain these actions by requiring that physical data should be preserved. So in this case, if we have some action like this, what are the constraints that this action should satisfy so that we can call it a non-invertible symmetry? So that is what I will discuss next. So what are some conditions on S? One natural condition is to require that the topological spins are preserved. So if NSAB is non-zero, that means the line A and B can form a junction on the surface. Spin is preserved. Another condition is a generalization of the fusion condition that we had in the invertible case. Suppose we have A goes to B and C goes to D under this surface now, which is a non-invertible surface. Every time we have a non-trivial configuration like this, we can fuse the lines on the surface and get a configuration like this on the right-hand side. The possible junctions alpha here belongs to a vector space of dimension NSAB, and possible betas here belong to a vector space of dimension NSCD. So every such choice gives us some non-trivial right-hand side. So there is some inequality which relates these junction space dimensions that we have here. In the case of an invertible symmetry, this was an equality. In the case of a non-invertible symmetry, this is a inequality, because sometimes on the left-hand side you can have zeros. Sometimes A cannot be mapped to a line, so this is 0. But here on the right-hand side, it could be 1. So this is why it is crucial that we have this inequality here. So that is a generalization of the fusion rule compatibility that we had in the case of invertible symmetries. Also, we have this condition that the sum of these coefficients NSAB is equal to the number of line operators. So this is saying that some of the line operators can be set to 0, that is allowed, but the total number of non-trivial such junctions should be equal to the number of line operators. This is something that you can show is required by requiring that this NSAB, you can think of it as a matrix in A and B, and requiring that this should commute with the S matrix or the braiding matrix. You can prove that this should be true. So the S matrix was called B in the data that I used. So this tells us that this should be satisfied. So these are some conditions that we have, and this is the 3 conditions that tells us that the action of the surface is actually a non-invertible symmetry. And this is a way of describing something that is already known in the literature, which is that whenever you have a surface operator, you can in a theory C, you can fold the theory to get a gap boundary of C times C bar. So whenever you have a surface operator in C, you can fold it and you get a gap boundary. And whenever you have some junction of operators A, B on the surface, the junction of line operators now becomes a junction on which A comma B bar ends on the gap boundary. So these conditions 1, 2, 3 is nothing but saying that when you fold this theory, you get a Lagrangian subgroup, because gap boundaries are classified by Lagrangian subgroups in this abelian TQF case. And these 1, 2, 3 conditions are essentially telling us that if you fold this picture with the surface operator, you get a Lagrangian subgroup. So that is what these conditions mean. Okay, any questions on these conditions? Okay. So yeah, so this is precisely the Lagrangian subgroup. Now we can ask, we looked at the action on line operators. What about the action on fusion spaces? So line operators can form junctions, and the surface operators can also act on the junctions. So we have some picture like this where we have some surface operator here, and if you take the surface operators across a junction, you have some matrix acting on the fusion space, the junction. And what about these actions? But in the case of abelian TQFTs, these actions are completely fixed by the action on line operators. So if you specify an action on line operators satisfying the 3 conditions in the previous slide, you can uniquely fix these up to basis transformations on the junction space. And the reason is that we know that in the folded theory, a gap boundary is completely fixed by a choice of bosons, which forms a Lagrangian subgroup. And that is all the data we need to fix the gap boundary. We don't need an additional data. So we don't need to specify these in addition to the 3 conditions that we had before. These can be computed from the surface operator action on line operators. Okay. So a terminology that I will use is that the surface will be called invertible if its action on the line operators is a permutation. So this is in agreement with what we discussed earlier, that we have this permutation action on line operators when we have an invertible symmetry. Usually this invertibility of a surface is defined using fusion rules. We can define it at the level of the fusion rules. And here I am defining invertibility at the level of the action of the surface on the line operators. And these 2 notions are equivalent as long as you don't have surfaces which are unfaithful. So if you only have surfaces which act faithfully, that means the only surface that acts trivially on everything is the trivial surface. If you assume that these 2 notions are the same. So here I am focusing on the action of surface on line operators. So therefore, I will use this definition of invertibility and go forward. Okay. So what are some constraints on possible surface operators? So we discussed a generic surface operator action on lines. We discussed some conditions that the surface operator should satisfy. And we can ask what are some conditions on this. So the claim is that a non-invertible surface operator must take a simple line to a non-simple line. So this is not, we could imagine an action on line operators where each line is mapped to some other line, but still the action is non-invertible because you can have a bunch of lines mapped to the trivial line, for example. So in other words, if you take the group of line operators, the abelian group of line operators, instead of having an automorphism, you could have an endomorphism of the group. In that case, you don't take a simple line to a non-simple line. And the question is, can that happen? And the claim is that that cannot happen. And how do we see that explicitly? The point is that if the surface acts and takes every simple line to a simple line, the surface cannot set any line to 0. You have a non-trivial action on every line, and for every action on every line, you have a unique outcome. Then the inequality becomes an equality. So there is no zeros that can appear in the inequality in the definition of the surface operator. It becomes an equality. And in this case, we can show that there exists at least some line, non-trivial line, such that it is mapped to 1. Why is that required? Because we want to assume that the surface operator is actually non-invertible. So if the surface operator maps simple lines to simple lines, and if it is also non-invertible, it should map some non-trivial line to the trivial line. So we call that line E. And that line must be a boson because we know that the spin should be preserved under the action of the surface operator. So there is a non-trivial boson in the theory. Now, that leads to a problem because if you consider this surface operator action here, S acting on A for some line operator A is equal to S acting on A times E, because S acting on E is just 1. And this equality means that the spin of A and the spin of A times E is the same for all A. And that leads to a problem with modularity. So if you compute the S matrix for E and A, where E is this fixed boson that we get from this here, we find that there's a row of the S matrix which is same as the row of the identity matrix. So this is degenerate, which is inconsistent with modularity. So this is one way in which we see that a non-invertible symmetry should necessarily take a simple line to a non-simple line. And what this also means is that we had this constraint that the sum on NSAB AB, the sum should be equal to the size of the group. So if a non-invertible symmetry necessarily takes a simple line to a non-simple line, this constraint of the sum being equal to mod A implies that there exists some line operator which is set to 0. So call it C. So a non-invertible symmetry always sets some lines to 0 and always maps some other lines to a sum of lines. So this is the lesson from this. Any questions on this? Okay. So let me go ahead and say that if we have non-invertible symmetries, there should be bosonic line operators in the theory. And why is that true? The reason is that suppose we have a non-invertible symmetry, then we learn that there exists some line operator A, which is mapped to a sum of lines. You cannot map simple lines to simple lines. It's a non-invertible symmetry. So there exists some A such that A goes to B1 and A goes to B2, and both are non-trivial, and where B1 and B2 are not the same. And using this, we can show that, and use definition of the surface operator, you can show that the trivial line should be mapped to B1 times B2 bar. So B1 and B2 are distinct line operators. So B1 times B2 bar is never the trivial line. So what we learn is that if you have a non-invertible symmetry, the trivial line should be mapped to some non-trivial line. And this non-trivial line should be a boson because this actually preserves the spin. So this is why we always find a non-trivial bosonic line whenever we have a non-invertible symmetry. And what this implies is that we can consider abelian TQFTs without bosonic lines, and all of those TQFTs are precisely the ones which do not have any non-invertible symmetries. And mathematicians have actually considered these modular tensor categories which do not have bosonic lines, and they are called anisotropic pointed categories, which are considered in this paper. And in fact, there is a full classification of such categories. So that using this result, that is actually a classification of all TQFTs without non-invertible symmetries. Yes.
How much of what you said so far applies to abelian theory and how much is non-abelian?
Yeah, so it will be true that even in non-abelian, you would need bosonic line operators, but it is not enough to have bosonic line operators. In non-abelian theories, you have to ask whether the bosonic line operators can be condensed or not. In abelian theories, bosons can always be condensed, but because that is not true in non-abelian, we will actually get the same constraint, but
I'm sorry about my ignorance. What do you mean by condensed?
Yeah, so the one-form symmetry of that line operators is non-anomalous. So that will be a condition that we have in non-abelian TQFTs.
You mean that you can gauge the one-form symmetry?
That's right.
And in
in
the non-abelian case?
Yeah, so here being bosonic implies that we can gauge the one-form symmetry. In the non-abelian case, we will get a similar if and only if statement, where we will have to write condensable bosonic line operators or gaugeable bosonic line operators. So in the non-abelian case, the statement is that non-symmetries exist if and only if you can condense. There are bosons which can be condensed. All bosons cannot be condensed in non-abelian TQFTs. Yeah. So there is a very similar statement there also. Okay. Yeah. Conversely, so I explained this arrow here when we go from a non-invertible symmetry to bosonic line operators. If we have bosonic line operators, we can always define a non-invertible surface. So if we have a bosonic line operator B, take this group which is generated by that B, and we can define a surface operator whose action on line operators is given by the orbit of A with B. So what this means is that you just multiply the elements of B with A. So that is the outcome of the surface operator action if A braids trivially with everything in B. If A braids non-trivially, then you set this action to be 0. So in other words, the action of the surface operator is precisely the same as what happens when you condense or gauge this B. And you can check that this surface actually satisfies the three conditions that we had. And these are these universal surface operators, which were also discussed in these papers. Whenever you have some bosonic line operators, you can condense them on you can higher gauge them on a surface, and that produces a surface operator, and that surface operator is precisely this one. Okay, so that explains this if and only if here. Okay, so now let me go to this group, the notion of group theoretical non-invertible symmetries. So the idea is that suppose you have some abelian TQFT which may have some non-invertible symmetry, you condense or gauge all the bosonic line operators in that, you end up with some T prime which doesn't have any bosonic line operators. And if T prime doesn't have any bosonic line operators, have non-invertible symmetries. And condensing these bosons is precisely the topological manipulation which maps a theory with non-invertible symmetries to another theory without any non-invertible symmetries. One example is U1 at level 8 Chern-Simons theory, where we have 7 line operators, non-trivial line operators, and we have the spin for the line operators. And there is a surface operator which acts in the following way. The action of the surface operator on L0 and L4 is L0 plus L4, on L2 and L6 is L2 plus L6, and the action on the odd lines are 0. So this is a non-invertible symmetry in U1 at level 8. But you can condense this boson here, L4, and that takes us to U1 at level 2, which does not have any non-invertible symmetries. So this is the sense in which we say that all non-invertible symmetries of abelian TQFTs are group theoretical, in the sense that you can always do a topological manipulation and map it to a theory which doesn't have non-invertible symmetries. And the inverse process is always gauging a group, because we have an abelian TQFT, this condensation of a bosons is condensing some one-form symmetry. It's a group-like symmetry, and the inverse process of going from tau prime from T prime to T is also gauging a zero-form symmetry group. So that is why it's a group theoretical non-invertible symmetry. Okay. Now this leads to some natural questions. One is we didn't discuss about condensations in specifically. We defined these surfaces. We defined some notion of action on line operators, and we looked at some examples. But all surface operators of TQFTs come from condensations. So that leads to some questions. So I will use the following notation. SG sigma is a surface operator that is obtained by condensing some one-form symmetry G on some 2 manifold with some discrete torsion sigma. So that is a surface. And such surfaces exhaust all surface operators in a TQFT. So this leads to some questions. Given a surface operator using its action on line operators, how do we know which condensation we have to do to get that surface operator? So that is one question. So given these NSAB coefficients, how do we know which G and sigma to choose so that the higher gauging gives that surface? Another question is, if we have an abelian TQFT that do not have bosonic line operators, we learned that such a TQFT only has invertible symmetries. So in that TQFT, all condensations lead to invertible surface operators. Why is that the case? Finally, if we have abelian TQFT with bosonic line operators, we can still have some invertible symmetries. All surface operators may not be non-invertible. When do we know, when do condensations give invertible surfaces and when do they give non-invertible surfaces? So here I mean gauging on a surface to produce a surface operator. So that is how I'm using the word condensations here. A bit confusing, sorry, with the previous description. Here I mean, when do higher gaugings on a surface give surface operators which are invertible compared to non-invertible surfaces? So to answer these questions, we can look at the action of condensation defects on line operators. So we know that we can consider the action of surfaces on line operators in the following way. If we have a surface operator like this, which is obtained by condensation, SG sigma, every time we have some A and B, which can form a junction, This defines a modular invariant for a CFT using the Chern-Simons theory and CFT correspondence. So every surface operator gives us a modular invariant partition function. And for these particular surface operators which come from higher gauging, these are simple current modular invariants for the CFT described by this G and sigma. So the action of the surface on line operators in this case is precisely, yes.
Is there another condition on all these data so that even with the surfaces, you have modular covariance, or does this follow from the previous conditions?
The previous conditions imply that there is, modular invariance. Yeah, it commutes with the modular data. Yes.
Including with the surface? Or do you need to add anything else when you have the surface?
Yeah, so what I mean is that these integers here as a matrix does commute with the modular data. Just that follows from the definition. Okay. So and such simple current modular invariants have been completely classified. Which paper has the proof that unit level Chern-Simons theory does not have any non-invertible symmetries? Yeah, so that you can prove by looking at, you can try to use, one way is to apply the definition of the symmetries that we discussed and apply to unit level 2, and you will find that there is no way to have a non-invertible symmetry. Another way is to try to do all condensations, the higher gauging of lines in that case. And there is no non-trivial higher gauging you can do in unit level because there is an anomaly to higher gauge. So there are no symmetries at all for unit level, invertible or non-invertible. So that is two ways in which you can see it. Okay. So the action of a surface operator on a line A is given by the sum here, where the sum is over group elements G, such that we have this A should belong to this JG, which is like a set. And the sum is determined by the set JG, and the set is defined as follows. So this description comes from the classification of simple current modular invariants. So the set JG is defined as follows. For every G, we check whether this condition is satisfied. So this is the braiding matrix, and this is a phase defined here, and we do this equality for all group elements. And this phase can be found from the R matrix. It can be found from the R matrix and tau and sigma. Sigma is the discrete torsion that we have here in the surface. Tau is defined as a trivialization of the F symbols on this group G, which is also gauged because G can be higher gauged. So this is a description of simple current modular invariance, and we can use this to study the action of condensation defects on line operators. So this is the general expression. So one thing is that we can do is we can actually start from the action of surface on lines and reconstruct the group and the co-cycle. So these are two formulas that tell us how to reconstruct the group from the data of the surface operator action. So let me actually explain it in an example to make it explicit what I mean here. So whenever you have NSAB non-zero, what you do is you fuse B and A bar. So whenever NSAB is non-zero, you fuse B and A bar, and the set of such B times A bar is the group that you need to condense. And once you find the group, you can apply this expression, which is just inverting the modular, the simple current partition function expression. So we have this expression here. We can use this, the R matrix, the braiding matrix, the tau, etc., and find the discrete torsion as well. So let us look at an example of surface operators in Z2 discrete gauge theory. So in this case, we have 4 line operators, and we have a fusion group, which is Z2 times Z2, and all of them are bosons except for one fermion. In this case, we have a line operator, we have a surface operator S1, which acts as an invertible symmetry, which is the electromagnetic duality surface. And which lines do we have to higher gauge to get this surface? So here the idea is whenever SAB is non-zero, you fuse B with A bar. So here we see that E and M are related by the surface. So you fuse E and M bar, but here everything is self-dual, so you just fuse E and M. If you fuse E and M, you get psi. So the group G contains psi. So if you do it for each of these surface actions, you will find that the group that you need to higher gauge is precisely this order 2 group 1 comma psi. And we don't have any discrete torsion in this case because it's a Z2 group. Similarly, we can consider other surfaces. There is another surface operator. And using this action and using this formula, you can find that you have to higher gauge the full set of line operators on a surface with trivial discrete torsion to get this surface operator. And crucially, determining the sigma requires us to write down the R matrices, and that depends on a basis. So you have to choose a basis and write down the R matrices, and that will then specify the sigma for us. And for a particular choice of the basis, we get sigma is trivial in this case for this surface. There is also another non-invertible surface which acts in this way. And if you use this formula, you find that this is the group that you need to higher gauge, but you have to now choose a non-trivial discrete torsion to get this surface. So this is how you go from the surface operator action to the data that you need to higher gauge. And if you look at this correspondence of surfaces with higher gauge, the data to higher gauge, this is an agreement with this paper, where they find these surfaces using higher gaugings. So this is an example. Any questions on this so far? Okay. So what about invertibility of condensation defects? When do condensation defects act invertibly on the line operators? So as we discussed, this is a question about asking when is the action of surface on lines a permutation? Or in other words, when is the simple current modular invariant of the CFT a permutation modular invariant? That is the question that we are asking. In fact, that can be answered as the statement. This condensation defect is invertible if and only if this phase that we defined in terms of the R matrix, this tau and sigma, this phase should be non-degenerate. If this phase is non-degenerate, this is always an invertible surface because the action on the lines will be a permutation. I will not describe the proof of the statement. I'm happy to discuss this at the end. Let me actually discuss an example so that this becomes clear. So one example is when G only has bosonic line operators in it. When G only has bosonic line operators, this R matrix can be set to 1. And even the tau can be set to 1 because the F and R matrices can all be set to 1 if G only has bosonic line operators in it. And then the non-degeneracy of this phase is completely determined by sigma. So whether you can choose, if you choose a non-trivial enough discrete torsion, this phase will be non-degenerate, and then that guarantees that you can get invertible surfaces. So even though you are higher gauging bosons, you can get invertible surfaces for some choice of discrete torsion. Another example is G equals Z2, where you have discrete torsion, and you can also again set F to be trivial on that Z2, and therefore the tau is also trivial. So if you choose G is Z2, the only non-trivial factor is this R matrix sitting here. And for invertibility, we require this phase to be non-degenerate. So for invertible surface, we want this to be non-degenerate, which implies that RKK, which is a diagonal term, where K is this non-trivial line here, should be -1. So this RKK can only be plus or minus 1 because we require that the F is trivializable. And for the non-degeneracy of this phase, this spin should be -1. So if you higher gauge Z2 boson, you get a non-invertible surface. And if you higher gauge a Z2 fermion, you get an invertible surface, and which is again described in this paper. And the non-degeneracy of this phase is a generalization of that condition. Okay. Any questions on this? Okay. So let me finally go to non-abelian TQFTs, where we have to be more careful about defining symmetries. So a natural generalization of the definition that we had for abelian TQFTs, we can try that natural generalization in this case. Again, we require that whenever the surface operator action is non-trivial, we require the spins to be preserved. Now we have a generalization of this inequality that we saw in the case of abelian TQFTs, where if we have a junction of two lines on the surface, A goes to B, C goes to D, we can fuse and get another junction here. But this fusion of A and C does not produce a unique outcome. We have a non-abelian TQFT. So E and F can take different values. So the inequality that we had in the abelian case has some fusion coefficients now here, sitting here. So there is still an inequality, but here the right-hand side is slightly more complicated because now we have a sum of terms on the right-hand side described by the fusion coefficients A, C, F, and B, D, E. This is also a natural generalization of the condition that we had in the abelian case. Similarly, we also have this, in some sense, a completeness relation where we say that, okay, the surface can set some lines to 0, but this sum should give us the dimension of the category that we have. So again, when we do a sum over these coefficients, we get the dimension of the category. So there's a completeness relation that we have, similar to what we had for the abelian case. Now we can try to use these conditions and describe symmetries of non-abelian TQFTs. But one problem is that charge conjugation, which is taking a line A to A bar, always satisfies these three conditions. Charge conjugation always satisfies these three conditions, but charge conjugation is not a symmetry of some TQFTs, as proved in this, as given in this paper. There are some examples of TQFTs for which charge conjugation is not a symmetry, even though it satisfies all of these conditions. So our definition is incomplete. We need to add some more data, some more constraints. And that constraint comes from the fact that we haven't taken into account the action on fusion spaces now. So we have to take into account action on fusion spaces. So we saw that whenever we have A goes to B and C goes to D, we can fuse these lines on the surface to get configuration like this, where now we have E and F related by the surface. But now we have to define some morphisms between these spaces that we have. So whenever we have A, C, we fuse it to, we have this junction here. B, D, when we fuse it, we have this junction here. So the condition that we had of fusing lines on a surface, in this case, we have to also require that there are these morphisms, these F tildes now, between these two diagrams, which are giving us some morphisms between these junction vector spaces and also this junction vector spaces here. So this is an extra data which is actually not fixed by the action on line operators. And this data is actually known in a different language. So we know that whenever we have a surface operator, we can fold the theory and get a gap boundary. And for non-abelian TQFTs, the gap boundary is described by a Lagrangian algebra now. It may not be a subgroup. And this F tilde is known in the literature as what is known as M3J symbols. So this F tilde, so if you fold this diagram, you get the following. So you suppose B is the gap boundary corresponding to the surface. Once you fold the picture, you have two line operators ending on the gap boundary. You can end them parallelly like this, or you can first fuse the lines and end them on the gap boundary. And there is a map between these two. And this map was called M3J symbols in this paper here. And this is precisely the F tilde in the unfolded picture. And this F tilde is crucial information because even if you define some surface operator action which satisfies the three conditions in the previous slide, there may not be a consistent F tilde. So what are the consistency conditions on F tilde? We cannot choose F tilde arbitrarily. There are some consistency conditions which come from associativity and braiding again. So constraints on F tilde come from, one constraint is this commutativity diagram that we have. So we start with three lines passing through the surface. We can apply the F tilde map to get this, and we can again apply F tilde to get this here on each pair of lines. We can apply F tilde to get this here, again apply F tilde to get this diagram here, we can go from this diagram to this diagram using F moves, which is different from F tilde. F moves for the F matrix that we defined earlier. So you can apply F moves on either side to go to this diagram here. So we get a commutative diagram which constrains F tilde in terms of the F matrix. So you have to use the F matrix to solve for F tilde, which satisfies this condition. Also, there's a condition from braiding, and that is that if you braid two lines, pass it through the surface, and again braid them, this should be the same as not braiding at all. So you can have this lines getting acted on by the surface with and without braiding. And in the folded picture, this is again saying that if you have two line operators which are braiding and ending on the gap boundary, this should be same as just ending on the gap boundary. So there are these conditions from commutativity as well. So essentially, this condition here, the braiding condition requires that the condition that the Lagrangian algebra is actually a commutative algebra. And this condition here tells us that the Lagrangian algebra is actually associative algebra. So there are these extra conditions on F tilde. And the point is that even if you choose some action on line operators, there may not be an F tilde which satisfies these conditions. That is why some naively written down symmetries are not actually symmetries of TQFTs, like charge conjugation. Okay. So basically what I'm going to argue now with the time left is that with this definition of non-invertible symmetries of non-abelian TQFTs, we can argue that again, we should have bosonic line operators to have non-invertible symmetries. To see this, suppose we have a TQFT without bosonic line operators. Again, this is a non-abelian TQFT now. So without bosonic line operators, and what we immediately learn is that the action of the surface operator on the trivial line cannot take you to any non-trivial line. And no non-trivial line can be mapped to the trivial line because there are no other bosons and action should preserve the spin. So if you don't have any bosons, the action on the trivial line only gives the trivial line. And we also know that these NSABs as a matrix commute with the modular S matrix of the theory. That is something that can be proven from the definition. So NSAB as a matrix commutes with the modular S matrix. So we get this condition, commutativity condition. And we can use this condition and look at some special cases. Suppose we choose B to be 1. So we choose this B here to be 1. Then the left-hand side, we can apply B to be 1 and use this delta function here. And the left-hand side collapses to just a quantum dimension of A. And the right-hand side becomes a sum over quantum dimensions, DC. So this is how this expression simplifies if you set B equals 1 and if you use this delta function condition. Similarly, if you set A equals 1, you get a similar relation, which is saying that the sum over C DC is DB. So you get these two conditions as some special cases of this commutation with the S matrix. And these two conditions, if you want to simultaneously satisfy them, there is only one option that you have. For unitary TQFTs, the quantum dimensions are always greater than or equal to 1. And for these two conditions to be satisfied together, the only choice is for the surface operator to act as a permutation. If you map some line to a sum of lines, then there will be an oversaturation of these conditions here. So this is, for example, telling us that the sum of quantum dimensions of the output of the surface operator action should be equal to the input quantum dimension and vice versa. So there is only one way this can be true, is that it can be a permutation, but that's it. So what we found is that the action of a surface has to be a permutation if we require that this condition is satisfied, which we automatically got in this context because we were looking at a theory without bosonic line operators. So the action of the surface on line operators is invertible because it's a permutation. But can we call it an invertible symmetry? Naively, we could imagine a scenario where the action of the surface on lines is a permutation, but somehow the action on the fusion spaces is non-invertible. Is this possible? Is one question that we can ask, because as we saw in non-abelian TQFT, the action on fusion spaces is not determined by the action on lines, we have to use that along with some constraints. This F tilde matrices have to be found. And the question is whether the action on fusion spaces can be non-invertible, even though the action on line operators is a permutation. And the answer is no. If the action on operators is a permutation, the action on the fusion spaces is also an invertible action. So I have an argument here, but I will not go through the details because it's already 1 hour, I think. So the basic point is that if the action of the surface on line operators is a permutation, the action on the fusion spaces is also invertible, which you can show by starting with this diagram and using some consistency conditions. You can move the surface to one side and you get the action on the fusion spaces, and you can use this consistency condition to show that in fact the action on the fusion spaces should be an invertible matrix. But this can be shown, and the point is that if a TQFT does not have bosonic line operators, the action of a surface on lines and fusion spaces have to be invertible. Okay, so this is what we found. If we don't have bosonic line operators, the surface acts invertibly. Now we can ask if there is a non-invertible symmetry, are there bosonic line operators? And in fact, this is true. So suppose we have a non-invertible symmetry. What we learned is that one of these should be non-zero. So NS1A or NSA1 should be non-zero. This is because if this were both zero, we already saw that the action of the surface on lines and fusion spaces is invertible. So to have a non-invertible symmetry, one of these should be non-zero. Using this, we can define two sets of line operators. We define the set AL, which is a set of line operators which is mapped to 1. That is the set AL. And we define another set of line operators AR, which is a set of operators which is mapped, the trivial line is mapped to A. In that case, you put A into this set AR. At least one of these sets is non-trivial. These sets always contain the trivial line, of course, but there will be a non-trivial line in at least one of these sets because this condition is satisfied, because we have a non-invertible surface. And these are two sets of bosonic line operators that we have. AL and AR are two sets of bosonic line operators. So already we see that if there's a non-invertible symmetry, again, there should be bosonic line operators. But the statement is actually stronger than that. This AL and AR can be shown to admit the structure of a commutative Frobenius algebra. So in other words, AL and AR are not just bosons, they are gaugeable bosonic line operators. But AL and AR may not be a subgroup, they may not be a subcategory, it could be some algebra. So that is why I've written here some Frobenius algebra. But it can be shown that these line operators are not just bosons, but they admit the structure of a commutative Frobenius algebra. So in physics terms, it means these are not just bosons, they are gaugeable bosons, which is shown in this paper. So this tells us something interesting, that existence of bosons is not enough to have non-invertible symmetries. The bosons should be condensable or gaugeable. Let us see that in an example. So we have the Fibonacci category where we have 1 and tau as the line operators. Tau times tau is 1 plus tau. And we have this particular spin. We know already that this Fibonacci category do not have any non-trivial bosonic line operators. So the Fibonacci category does not have any non-invertible symmetries, just from the fact that there are no non-bosonic line operators. But we can take 5 copies of the Fibonacci category, just stack it on top of each other. Then the 5 copies of this tau line is now a boson, because this is the 5th root of unity here. So if you take 5 copies of the Fibonacci category, that category has a bosonic line operator in it, but it is known that that line operator cannot be condensed. It is proven in these papers that that line operator do not admit the structure of a commutative Frobenius algebra. So even though you have a boson, you cannot condense it. So 5 copies of the Fibonacci category, even though it has a bosonic line operator, it doesn't have any non-invertible symmetries. So that is what we learned from this. Any questions on this example? Okay. So yeah, and also it's an if and only if statement because if we have some condensable bosons, so B is a set of bosons which we can condense. So it's a non-anomalous one-form symmetry, some non-invertible algebra type symmetry. Then we can define a surface operator like we defined it in the abelian case, where the image of the surface operator action is image of this line A under condensing B. So what happens to A under condensing B? If A braids non-trivially with these bosons, it could be confined. We could project out A. In that case, the outcome of the surface operator action is 0. But in general, A could actually be put into an orbit under condensation. And in that case, the outcome is that orbit. So this is why what I mean by defining the surface operator as the image of A under condensing B. So this is a surface operator that we can define for any non-anomalous one-form symmetry. And in particular, this is non-invertible because we know that this surface will set some lines to 0. In particular, the action on the trivial line is actually the sum over all these bosons. So it is definitely a non-invertible surface. This can be proved This can be proved explicitly by noting that this SB is obtained by higher gauging these lines on a two-manifold. So you can higher gauge the bosonic lines here, which is now an algebra type one-form symmetry on a two-manifold and get a surface. And you can show that that surface acts in this way, and that is a non-invertible action. So this is a generalization of the universal surface operators discussed in these papers, where they study non-invertible surfaces coming from Reb G subcategory. So this is a special case of this B, where we have a subcategory of bosons. But here, this could be any algebra type bosons. We still have some non-invertible surface operators. So far what we have seen is that non-invertible symmetries and condensable line operators or gaugeable line operators come in, one-to-one. Like essentially, it's an if and only if statement that non-invertible symmetries exist if and only if there are gaugeable line operators. Not to be confused with higher gaugeable line operators, but 2+1D gaugeable line operators. So this then again allows us to show that all these non-invertible symmetries are non-intrinsic, because again we start with some TQFT which has non-invertible symmetries. That TQFT is guaranteed to have bosonic line operators which we can gauge. So what we do is we sequentially gauge all the bosonic line operators one by one. So we sequentially start with T1, which has some non-invertible symmetries and has some bosonic line operators which can be gauged. We sequentially gauge till we end up with some TQFT which doesn't have any condensable bosonic line operators. And that Tn is guaranteed to have only invertible symmetries. And such Tn have a name in the math literature, and they are called completely anisotropic modular tensor categories. But I don't know if these have a class like in the abelian case. But some aspects of these Tn's have been studied in the literature. And this is in the sense in which we say that this is this topological manipulation we can do to map a theory of non-invertible symmetries into a theory without non-invertible symmetries. So that's the idea. But note that this is non-intrinsic, but it may not be a group theoretical. So remember that to be group theoretical, this inverse process of going from Tn to T1 should be gauging group-like symmetries, and that is not guaranteed. Sometimes these condensations are algebra condensations, and the inverse process in that case is not gauging a group. So this is an example of a non-intrinsic symmetry is not group theoretical. Group theoretical surfaces or no, group theoretical non-invertible symmetries are a special case of non-intrinsic in this definition, and they have been studied recently in this paper. Okay, this is the notion about non-intrinsic non-invertible symmetries. Okay, finally, let me say something about QFTs. So in QFTs, we have a set of line operators. I will look at the set of line operators which form a finite structure like a braided fusion category. So we have a set of line operators which form a braided fusion category. It may not be modular in a QFT. Now that braided fusion category can have a set of line operators which are completely transparent. So we could have a set of line operators A, which braid trivially with all the other lines. So that I will call A. And I will assume that all the transparent lines are bosons. This assumption is required because so far I have been looking at bosonic TQFTs. And to apply that story to this, here I require all the transparent lines to be bosons. But I think the results that I described can be generalized to spin. And in that case, we can allow these transparent lines to be fermionic as well. Here I will focus on transparent lines being bosons. So in that case, all the transparent lines in this braided fusion category D form some rep H type subcategory. So there is some bosonic subcategory of lines, which are all braiding trivially with all the other lines. So that is a set of transparent lines. So this is the setting we have. Now we can do the following topological manipulation. So condense this A. So this A is this rep H type subcategory. You can condense this A and you get this new category D mod A. And that is a modular tensor category because you have removed all the transparent lines by condensing them. And the resulting set of line operators will all braid not really with each other, and it will be a modular tensor category. So if you start with this theory here, you always have, if you have some transparent lines, you can condense them and always go to a modular tensor category. In other words, if you start with some theory with non-invertible symmetries, so D always has non-invertible symmetries if this rep H is non-trivial, because as we saw earlier, whenever you have this rep H type subcategory, you can condense, you can gauge them on a surface to get non-invertible symmetries. But you can condense them and go to this modular tensor category. Now what you do is you look at this D bar A, which is a modular tensor category. Look at if that category has any bosonic line operators or not, which are gaugeable. If you have gaugeable bosonic line operators, you gauge. So you do these two steps. One is condensing all the transparent lines to go to a modular tensor category. Then you condense all the condensable lines in the modular tensor category to go to another category. The resulting category M does not have any bosonic, does not have any condensable bosonic line operators. So any symmetry that acted non-trivially on D will act trivially on this M, because M as a modular tensor category does not have any symmetries. So this is a statement that we can say that if you start with this generic braided fusion category D of a QFT, you can do these topological manipulations to arrive at a category which doesn't have any symmetries. We can strengthen this statement using the following mathematics result. The statement is that any fusion 2 category is Morita equivalent to this category here. So physically, what I mean is that fusion 2 category describes the lines and surfaces of a 2+1D QFT. And Morita equivalence here means that there's a topological manipulation to convert any such fusion 2 category to a category of this form. What is this form? This is 2-vec G times mod C. What this means is that this 2-vec G is a set of surface operators whose fusion is just given by this group G, some finite group G. Mod C should be thought of as the lines and surfaces of a TQFT, because here C is a modular tensor category, and mod C is just the 2 category formed by the surfaces. So in other words, any fusion 2 category, you can do some topological manipulation and end up with this fusion 2 category, which has these invertible surfaces, and all the non-invertible surfaces are condensation defects sitting inside this factor here. But then now we can use all the results that we proved for TQFT to this factor here and condense all Bose line operators in this mod C, if we have any. And then the resulting fusion 2 category will not have any non-invertible symmetries. So we go from any fusion category to this particular form. This is proved in this paper. And in this form, you only have condensation defects as the non-invertible, potentially non-invertible defects. And then you use the results for TQFTs in this case and do one more topological manipulation to go to a theory which only has invertible surfaces. So it is in this sense that we say that non-invertible symmetries implemented by surfaces are non-intrinsic, even if we consider generic fusion 2 categories and QFTs with such symmetries. So because I've gone really over time, let me stop here with this conclusion slide. Sorry about going over time. Thank you.
Great, thanks a lot for this nice talk, Rajath. Are there any other questions? And one question of obvious is indeed what you put down here in higher dimensions, whether there's anything you can say generalizing this when you have actually two-dimensional surfaces, line operators, even three-dimensional defects.
Yeah, I think maybe for, because I think there is a way probably to extend this to higher dimensions, but I guess the non-triviality will come from membrane operators, because surface operators will always be non-intrinsic in 4 dimensions, because you can always gauge the lines and make the surfaces invertible. You can always gauge all the lines up to a transparent fermion, but that is enough to make all the surfaces invertible. So surface operators will implement non-intrinsic symmetries in 4 dimensions in general. But for membranes, it will be interesting to see whether that is true or not. Yeah.
Because I think there the statement isn't like this result that you're quoting from Thibault about this equivalence to 2 back box times mod C. That's not true.
Yeah, right. Yeah, I don't know. I'm not aware of.
You have sort of like in physics terms duality defects. So you have to
Right,
omit
exactly.
the symmetries.
Exactly. Yeah.
Any other questions? We've gone quite a bit over time, so everyone's a bit exhausted, but all right, I don't see any other questions. Let's thank actually Rajath again for his nice talk. And Purv, if you can also stop the